Conservative vector fields, Part 2. In Part 1, we defined what it means for a vector field to be conservative. A vector field F is said to be conservative if there exists a scalar function phi such that F is the gradient of phi. Now, if there does exist such a scalar function phi, phi is called the potential function of the vector field. Now, we found that if a vector field is defined on a connected and simply connected region where its components have continuous first partial derivatives, we found that if all of that is true, then the vector field is conservative if and only if these partials are equal. And in two-dimensional space, we only needed to check one condition. Then in Part 1, we determined that each of these vector fields are both conservative. Since they are conservative, they must each have a potential function. In Part 2, we learn how to find the potential functions. Let's start with the easier one. Find a potential function for this conservative vector field. We are looking for a scalar function phi such that f is the gradient of phi. If f is the gradient of phi, then phi partial x has to equal f, and phi partial y has to equal g. So we know what phi partial x is. If we integrate that with respect to x, that might get us someplace. So that's what we'll do. We integrate with respect to x. Now notice when we integrate with respect to x that the constant of integration is an arbitrary function of y. And the reason is that phi, keep in mind phi, is a function of both x and y. So integrating with respect to just x, my constant of integration might involve y. So I have to write it that way. Now we want to know what that constant of integration is. So we're now going to differentiate what we found, but we'll differentiate with respect to y. And this is what we get. We find when we differentiate with respect to y, we get this. Now we know what phi partial y must look like. It must look like g. And so we must have this matchup, which tells us that c prime has to be 0. So if c prime is 0, then c would be, the function c would be a real number. Now any real number will work, and we're going to choose 0. So we can check that phi, this phi that we found, is a potential function for the conservative vector field by checking that f is the gradient of phi. So you might want to turn off the video and just check that right now. Now let's do the harder problem. This, as you might guess, will involve more complicating features, but it's the same idea. We're going to find a potential function for this conservative vector field. Again, we are looking for a scalar function phi such that f is the gradient of phi, which means that phi has the property that phi partial x is f, phi partial y is g, and phi partial z would have to be h. So whatever phi we find, it has to satisfy these three equations. Well, let's start with phi partial x having to be f. What we'll do is we'll take that and integrate with respect to x. And when we do that, keep in mind that the constant of integration is an arbitrary function of both y and z. After integration, this is what we get. Now just check. Now c, our constant of integration is in terms of y and z, but check, its derivative with respect to x would be 0. All right, and so just check here that this phi, if we take the derivative with respect to x, that we would get f. Okay, we're now going to work on finding this constant of integration. If we differentiate what we have found, if we differentiate that with respect to y, and use the fact that we know what phi partial y should look like, then we discover that the c partial y would have to be 2z. All right, so this is where we are right now. We know that phi looks something like this. We also know that the constant of integration, c, we know what its partial would have to look like. Next, we're going to integrate c partial y with respect to y. Now, this time the constant of integration will be a function of z. And the reason for that is c is a function of both y and z. So if I take c partial y and integrate with respect to y, I might have something that is a function of z. All right, so go ahead and integrate c partial y with respect to y, and I get 2zy plus d of z. Now, plug this in for what we have so far for phi. All right, so now what do we know? Now we know that phi looks like this, and there's some leftover piece we need to figure out. What is the constant of integration, d? To find d, we differentiate with respect to z. Next, we use the condition that phi partial z has to look like h. And we do a comparison and discover that d, the derivative of d with respect to z would have to be 0. And so that means that d is a real number, and we can choose any real number we want, and I'm going to choose the easiest one of 0. So we conclude that this phi is a potential function for the conservative vector field f, and we can check our work by confirming that f is the gradient of phi. We're going to pick up this conversation again in part 3. I'll see you then.